In this lecture, we will learn about the astronomical spectroscopy. So first, what is a spectroscopy? It's the measurement of photons as a function of their energy level. The two in real the practice to measure the photons energy, so that actually we can eventually, I think, measure the intensity of the photons as a function of its wavelengths or as a function of its energy level. We need to physically separate photons into the different physical position. So the very action that actually that sorting the photons as a function of their energy level at different physical locations, such as the different position on a screen or different position on a detector, that action is called dispersing the light. Based on the specific design of the dispersing element, and then the way that actually we combine this dispersing element with the recording device, they generally that actually the spectroscope instrument in astronomy fall into the three different categories. First one is the one that actually we are seeing through. Okay? The first one is called spectroscope. The very end, that is, scope means that actually we are seeing seeing through that device. So think about the kaleidoscope. So on the instrument that actually dispersing the light, but actually we are seeing through that eyepiece. That's the spectroscope. That is actually used in the beginning of the astronomical spectroscopy many hundred years ago. But nowadays, actually, that spectroscope is not used in the real or the observational setup. Second is a spectrometer. It is actually a measurement device that actually measures the intensity at different wavelengths or different energy level of the incoming photons. So it is actually a measuring device, but more nowadays actually because of the using the 2D digital the detector, many of the spectroscopy instrument in modern day astronomy can fall into the category of spectrograph. It's basically the recording device of the spectrum. So dispersing the light and record the spectrum. So modern day the spectroscope element are mostly nowadays they categorize. And in spectroscopy, the itself can be fall into the two different categories. One is the dispersive spectroscopy, meaning that actually we are using some of the element, the optical element that actually disperse the light, so that the different energy level photons are actually falling in the different physical location. So that dispersive the element, many of them actually are used, and then most typical the example of dispersive element is prism that actually we will be talking about the following slide. Second is non-dispersive spectroscopy, meaning that actually it is not using the dispersive element, but it is actually using the wave nature of the photons, so that actually we are using interferometry, the so that actually we can separating the photons, and then based on their energy level by using the wave interference. So let's first look at the most simple and the time used dispersive element, prism. We know that actually prism with the incoming angle, okay, or incident angle of the light, or they enter into the high density spatial glass. And then this the material, glass material, prism material, has usually the higher refractive index than typical glass. So that actually higher the refractive index, it actually refract into the higher angle. So eventually, that actually that for the typical the triangular or the prism shape, the incoming photons actually refracted twice. One when it is actually entering into the prism material, and the second time when it is actually the escaping or the moving out of the prism material. And we know that actually dispersion, the index of refraction, and then the refraction angle is the function of the refractive index and also wavelengths, meaning that actually for the given material, short wavelength light refracted more. So meaning that actually that in 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 this the prism setup, the short wavelength light such as blue and violet or green light will be refracted more compared to the longer wavelength light such as red and orange. The meaning then for compared to this incident angle, if there is no dispersive element, all this light, regardless of their wavelengths, the incident light fall onto this look. Imagine that actually we set up a screen here. Okay? Because of the prism, that light is actually dispersed into the different locations, and we can actually think about amount of this angle, and wavelengths is increasing that direction, right, from the short wavelengths to the long wavelengths. So that's the wavelengths is actually that the increasing that way, and the theta is actually increasing this way. So we can actually think about the relationship between the amount of refracted dispersed light in terms of angle measured from the incident angle as a function of wavelengths. So this quantity, d theta over d lambda, is known as angular dispersion. Theoretically, is no same photons with no photons with different the energy level fall onto the same location, because it is no matter how that actually small the energy difference is, still that actually is separated in a different angle. The meaning that actually when we set up a screen and all this rainbow is actually projected on it, we should have infinite separation, and then all the light, all the photons should be holding on to this, even if there actually is a minuscule, very small change, it actually fall onto the different part of the screen. So that means actually we need to have infinite angular resolution, angular dispersion. Okay? However, because of the diffraction is happening because of this finite size and then abrupt change of the material, and also more the practically surface of this prism is not really perfect. There is a the undulations and then imperfection, meaning that actually there is the irregular, the refractions and different, the slightly different angles or not. So actually this d lambda is not infinitely small in practice. In practice, we can actually say that actually this d lambda is not infinitely small, but because of these imperfections and then diffractions or not, is instead of actually the one particular light is actually falling the delta function on the screen or the detector, that's actually spread over multiple pixels, multiple physical locations. But this finite amount of spread or the single wavelength can be actually described as the delta lambda. Okay? So this delta lambda is the practical limit of the actual the measurement. Okay? So when we talk about how strong that actually dispersion is for the given the spectroscopy the instrument, we are actually defining the term ratio called capital R, resolving power. Resolving power is actually defined as lambda over delta lambda. So when the delta lambda is smaller, we can actually have we separate very small or distant the photons with the tiny energy difference. We can separate those photons. So larger the resolving power, it is actually dispersing the light better. Okay? In a typical the modern day astronomical spectrometers have visual beam power values in the range of 10 to about 100,000. Sometimes actually you need actually very low spectral resolution, meaning that actually low visual beam power, so that actually you can cover a really wide range of spectral range. Sometimes actually you need really high visual beam power, such as like 100,000. The visual beam power typically used in a modern day the Doppler shift measurement, like the radial velocity measurement of the star. So this visual beam power versus the velocity, the resolution is actually uh, related to the the velocity of the object divided by the speed of light. Say that actually compared to the speed of light, which is 300,000 the kilometer per second, you want to measure, for example, like the 0.3 kilometer per second accuracy or precision for the velocity. So this is actually the kind of typical the size of the velocity velocity, the precision one should actually obtain to observe like Jupiter like the exoplanet in orbit around the star. Then 0.3 kilometer per second versus 300,000. So this basically give about 1 million visual beam power. So in the modern day, the visual beam power instrument oftentimes obtain like the 100,000 or 200,000 visual beam power. But then additional factor of maybe over 4 or 5 is obtained with the very sophisticated data reduction technique. Then the amount of dispersion or degree of dispersion when it is actually measured in terms of the angle, we are actually talking about angular dispersion. But when it is actually projected onto the screen or detector, then we can actually talk about the physical, the distance as instead of the angle theta. In that case, actually dx over d lambda is known as the linear dispersion measured on the detector. But throughout this, I think the first part, or most part of the lecture note, we will be actually focusing on the angular dispersion. Let's think it considers several possible dispersing elements. First one, as we have seen, is the prism. Okay, prism by using the refractive index material, it actually just really disperses the light into based on the wavelengths. Second, the category is so-called grating. When you actually or actually seeing the grading in spectroscopy, think about the compact disc CD. All of you must have seen the surface of the CD or DVD, and you see that as the surface of that CD or DVD has the regularly the spaced grooves. Okay? That grooves contains actually small lengths dot or some small, I think, finite lengths of arc. But nonetheless, there's actually one of the group to the next is very regular in spacing. When the light is actually being shined on the surface of CD or DVD, reflected light are interfering, and that is actually basically so-called the 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 diffraction grading, and then that is actually based on the reflected light interfering each other at the finite distance away from this the grading. And another way is actually that you can actually using the diffraction mechanism, or sometimes you can actually think about the transmittive materials that actually something like glass intermittently actually that the materials actually the refractive index is deliberately changed in a regular space. So that means actually that the transmitted light through this transmission grating are actually just refract regularly in a different direction, causing the eventually interference pattern. And so this is known as transmission grating, and there's a very special type of the reflection grating called Eshel or Eshel grating. And then this is actually is the device that actually they're producing really high resolving power. And then we will actually learn about details about Eshel degrading in the following video. Another one is actually that this type of prism. Okay? Look at this prism shape. Okay? This prism is actually attached in the entrance of the telescope tube, meaning that actually all the light actually coming into the telescope are dispersed. This is actually a great way to obtain low resolution spectrum of multiple objects in a single object. So this is known as objective prism, and I think the one example is actually shown here, and that actually that in a decent 1 meter, 2 meter class telescope, objective prisms are actually still being used infrequently. But as you will see in the special type of spectrograph, we have multi-object spectrograph that actually not using objective prism. Objective prism has the built-in limitations because entire object in a field of view is dispersed. So because the different dependent on the orientation of these two, the unrelated star, the spectrum can be actually overlap each other. Okay. Then lastly, that there's a special device called the Grism. This is the combined version of prism with grating. So this is the glassy material that actually forming this the triangle. The light is actually coming in from the left, so with some incident angle that is actually just coming in, okay, then refracted, and when it's actually exiting surface is actually the regularly graded. So meaning that actually that the 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 outgoing light are actually producing the interference pattern. Prism is used, I think, frequently in the modern day instrument, and the benefit of using the prism type of instrument, the element can be talked about later. Let's think about the prism in more detail. Okay, prism is actually that typical prism is actually defined by the single number called this angle, so-called apex angle. Okay? The angular dispersion as a function at the measured the angle of, compared to the incident angle of each the dispersed light, the d theta of d lambda is a function of this apex angle, okay, and incident angle, of course, and the refractive index, and also the function of wavelength system. Think about this, the prism. We all know that actually prism's dispersion is mediocre. It doesn't actually disperse that light into the really high the degree. So it is relatively low dispersion, okay? And then especially so in the long wavelength light. So the lower dispersion at the long wavelengths, and then in the high, this really high frequency domain, such as like the ultraviolet, violet cannot really actually transmit it through these glassy materials. So that means actually UV or even slightly higher far UV, they don't actually really can be dispersed through the prism. So low transmission in the far UV or near UV, and then of course then the higher the frequency light, such as like the X-ray, is simply just passing through this prism material. So low transmission in UV, UV is actually a block, so it is only limited to the optical wavelength. And when you are actually building the larger prism, the glassy material is very heavy, so heavier weight prism being attached into the instrument. That instrument itself, again, that actually attached to the telescope, and balancing the telescope or not is very complicated and the delicate procedure. So heavier weight of the prism is actually causing the difficulty. But in real practical usage wise, this amount of dispersion as a function of wavelengths not linear, meaning that actually that as you go to the longer, I think shorter and the shorter wavelengths, like this near to this blue light, they refracted in more. So the angular dispersion is inversely proportional to the wavelength's third power. So meaning that actually that they are actually progressively just dispersed into the larger angle when compared to the long wavelengths. So meaning that actually red, orange, and then yellow are actually jam packed together, very close. Yet green, as you go to the UV, toward the UV, the blue light, green, blue, violet are actually separated much better. So this nonlinear variation of angular dispersion and very poor dispersion at long wavelength light and very low or no transmission in UV and then heavy weight of prism has been the main difficulty in using prism. So nowadays actually that most of the advanced spectrograph in astronomy is using grading. So grading, imagine that actually that you are actually making a group repeated the same interval, well, the group actually be engraved into the reflected mirror, for example, or think about that as a very tiny strip of mirrors placed in a regular interval. Okay, let's think about that actually this slice of mirror reflects the element spacing spaced regularly with the spacing of sigma. So this sigma is so-called grading spacing or grading parameter. Okay? Then imagine that actually this reflected mirror is tiny bit rotated against the surface. This is the grading surface. Okay? Then each mirror is actually a tiny bit rotated. So that actually incident angle measured against this grading surface is called alpha. Then its reflected light is not at the same angle as the alpha they measured from the grading surface. So it has different angle. So that different angle is measured such as like the from the right angle, the normal against the grading surface, that the reflected light, the angle is actually measured all the way across. That actually has the theta. Then let's focus on these two beam. One, first beam, second beam. They are actually coming in parallel. Okay? Then all the way when they're actually the beam two actually they meet the reflective in the material, the beam one has yet to actually travel that much more, this much more the length. So this the path length difference for the first part. Path length difference is actually they can be written as AB. This length AB, when you actually measure, they think about this this is the right angle, okay, and this is also alpha, right? When you actually think about that, actually that and this is also right angle. So that means actually this is 90 minus alpha. Also that actually from here to there is actually right angle. So eventually this is actually this angle is alpha. So that means path length between A and B is sigma times psi. Then after reflected both light, okay, and then beam 2 need to actually travel this much. the length CD, this much traveled more to actually get into the same phase as the beam 1. The CD, okay, when you actually think about this angle, let's call this angle as a beta. Okay? Then this angle is 90 minus beta. And also that actually this is the right angle. Right angle. When you think about all these, then you can actually say, think about that actually this is actually the same as beta. Okay? Then in here, the beta is actually 2 pi. This is the beta, right? So beta is in fact 2 pi minus theta, meaning that actually that these lengths, the length between the C and then D point is sigma times sine of angle, which is the 2 pi theta. The CD, length CD is sigma 2 pi minus theta, which is actually minus sigma in theta. So that means actually net the path length difference between this reflected outgoing light of beam 1 and then beam 2 is the path difference AB minus CD, and then take the absolute value. Okay? Then this path length difference is basically sigma times sine alpha plus. Then this path length, if the path length difference is the integral multiple of the wavelengths, then this beam 1 and beam 2 at far away from this the grating surface, such as on the surface of the screen or detector, they constructively interfere. If the path length difference is integral multiple of half of the wavelengths, then they destructively interfere. So constructive interference condition is this quantity inside sine alpha plus sine beta is integral multiple, so that actually running number in integer times the wavelengths. And then the actually sigma is actually go to the right side. Then you basically have sine alpha plus sine theta is m lambda divided by. Here sigma is the groove state, the spacing. Okay? Then m is the running the integers 0 plus minus 1 plus minus 2. So 0, the light that actually that producing the actually that the zeroth order interference is called zeroth order, and the plus the first the order light or negative the order the first light. And in astronomy, that actually this group spacing or group the grading constant is actually that measured in a very tiny the unit, such as like the millimeter, fraction of millimeter. So oftentimes in astronomy, the instrument build that actually this group constant is actually just inversed, so that the instead of sigma itself, we can use the 1 over sigma, such as, okay, so per millimeter there is n number of groups, so such as like the 100 lines per millimeter grading, 300,000 lines per the millimeter. Higher the grading the numbers are, it is actually producing the smaller, I think, sigma spacing. But looking at the dispersion, the constructive instrument, the dispersion relationship, you can see that actually smaller sigma is causing it. Let's take one step back. So this is the constructive interference, the conditions, and differentiate. Differentiate this the equation as a function of lambda. Okay, the sine alpha for the given the observational setup, alpha is constant. So when you differentiate the constant, this is actually just theta. When you actually differentiate this, this becomes cosine theta, d theta. Okay? So on the right hand side, m is constant, sigma is constant for the given instrument. So m d lambda sigma. Then by rearranging this term, you can actually obtain d theta or d lambda, which is the angular resolution, is order number m, order integer m divided by sigma cosine theta. In the realistic the setup, the grading surface compared to the grading surface, screen or detector is located so far away, so that means actually the theta, so that actually beam 1 and the beam 2 are falling onto the same part, same physical position. That means actually the theta is actually, in that setup, theta is actually changing very slowly with respect to the lambda. So that actually this, the bottom number sigma cosine theta is nearly constant. So that means angular the resolution or angular dispersion is proportional to the order. So that means actually when you are looking at the higher order dispersed light, they actually produce a stronger, larger dispersion. And that is actually can be seen into the picture. This picture is taken through the transmission diffraction grading film. Okay, so when you actually see candlelight by using diffraction, the transmittive diffraction grading, center zeroth order is actually basically just appear as a non-dispersion. Okay? This is the reflected the light in the reflective grading. Then this is -1, this is +1 order, and then you can see that actually that the going into the higher the order, that light is actually dispersed more and across the larger angle. That is actually basically the behavior of angular dispersion proportional to the order number. Okay? And as you can see that actually imagine the next the order +4. If there is any that, and then you can actually start to can imagine that actually the blue light or the violet is actually starting from here, and the red may be ending here. So that means when you go to the higher and higher order, that light, the different wavelengths light are actually coexisting at the same angle. So at particular theta, multiple wavelengths can coexist. So this is actually known as the order overlap. So the light, different wavelengths light are actually coexisting in the same angle, meaning that actually different light actually that they coexisting. So that the range of spectral range that actually free of any disorder overlap, such as like from here to there, right? So there is no the overlap light from from here. There is no overlap, and if the force orders, for example, is standing like this, and from here there is actually no order. This is so-called the free spectral range. But utilizing only the free spectral range, greatly limiting the available space. Okay, so in practice, what we do is in the overlapped order location, such as like this particular light is lambda 1, another light is lambda 2. Before that, actually just projecting all this dispersed light onto the screen, put a special filter, such as high pass filter or low pass filter, such as actually blocking the wavelength light or below the green light, for example. That way you can actually effectively screen out one of the order, that particular the angle. So this is actually basically known as the order blocking filters. So that actually only one the wavelengths photons can be recorded in a given screen or detector. So the details of using these order blocking features or not can be actually they revisited in the second video. Before that, actually the wrapping up that actually the today's the video. Okay? Think about the advantages, disadvantages of using very simple design of prism versus grading. Okay, prism we already talked about the disadvantage. It is heavy, no UV transmission, and very small, I think low dispersion at long wavelengths light, and the dispersion relationship is not linear. Okay? So remember that actually d zeta over d lambda is proportional to the lambda third power, okay? Inversely proportional to the lambda third power. Is that gradings actually overcome many of these the disadvantages. Gradings can be actually measured in a very thin materials. Think about the DVD or CD. So the weight is not an issue. And this diffraction, it is based on the interference of light, the wave nature of the photons. So basically, in principle, they should work at every the wavelength, meaning they're actually ranging from really long wavelengths, radio light, to the all the way to the gamma, the ray, the gamma radiations. Then also, the actually good one is actually this the angular dispersion, or I think same as the linear dispersion. The angular dispersion T set of d lambda is not dependent on the wavelength, meaning that actually it is a constant. The angular dispersion is linear, so that actually spacing between the delta lambda. So if it is delta lambda is 2 angstrom, then the 2 angstrom difference light are actually in the red light domain versus actually blue light, they actually dispersed into the same amount of angular difference. So meaning that actually the angular dispersion is linear with respect to actually greatly simplified. But we already the seen that actually the problem of the overlapping nature. So the grading has the difficulty or disadvantage order overlapping, which requires the order blocking features. And the main the disadvantage of using gradings is because this imagine that actually this the imagine the intensity of this most light that actually simply undispersed and then just reflected into the zero source. This is undispersed, reflected light. Most energy is just dispersed, reflected into the zero the order, first order and then second order, and low orders are actually less. So when you need to actually just focus on the highly dispersed the light, you basically lose great efficiency because most of the light are wasted. Only maybe few percent level of light is producing that dispersed light in high order, such as order number 10 or 20, 30, and so on. So this loss of the efficiency is a great disadvantage of grading. But later on, there's a special technique that actually can recover, improve the efficiency of grading spectrum. And that more details and the different types of spectrograph will be the revisited, and then different types of spectrograph, actually very special design of grading spectrograph that capable of producing really high spectral the resolution or resolving power is known as the blazed degrading some combination of spectrograph, they produce really highly burst light, such as like 100,000 resolving power, and that is a field that actually used very massively, very widespread in modern day as Itiel spectrum, and then we will learn about in the following video.